Oh, okay, you want to know the speed at 2.
You released it, and the initial speed is 0 meters per second. Now when we release it, then gravitational pull takes over, right?
Right.
Okay, so when the gravitational pull takes over, this is where we need to understand what 9.8 what 9.8 meters per second squared means, or 32 feet per second squared means. Okay, so after a second, we drop this thing. Now, 1 second later, how far is the object? In a second, after 1 second after we release it.
32 feet.
Or 9.8 meters, right?
Or 9, right.
All right. After 2 seconds.
You just double it.
Okay, which would be what?
64 or 64 or 1.6. 19.6 meters per second squared.
I guess you were looking down. I have it there.
Yeah, sorry.
No, it's cool. It's cool. It's all right. So, this is the pylon that I'm talking about. Now, we did it in a horizontal fashion when I said, okay, your car started at 30 miles per hour, and then it finished off at 50 miles per hour. And then we were able to use the acceleration formula to come up with this. But with gravitational pull, if something just is released, we just need to know gravitational pull units, either 9.8 meters per second squared or 32 feet per second squared. And at 1, 2, 3, at 10 seconds. Now this is pretty cool. In 10 seconds, you should be able to answer this in 3 seconds. After 10 seconds of falling, how many feet in SI units or in US and in US has the object fallen?
Well, the feet's 320, and then the other one is like.
I'll give you a little trick. Just move the decimal over one place.
Right, 98.
All right, 98.1 meters at that point. So anytime we multiply something by 10, we add a 0 or we move the decimal over 1. All right, very good. Okay, so I think you have a clear handle on acceleration.
Yes.
All right. Now, so we have distance. Let's talk about speed. And I would like to know the speeds at 2 and 3 seconds of your object. In both units.
Okay, you want to know the speed at 2 and 3 seconds?
So you've released the object. And at 2 seconds, how fast is our object falling?
How fast is it falling? Well, that's distance over time. So 2 seconds, we're just doing it in feet. 64 divided by time is 3 or 2 seconds. That's 32 at 2, and the other one is going to be 32 times 3 is 96 over 3 seconds, which is like 31 to. Oh yeah, it's just 32 on both of them. 32. I don't know what the units. How you put that in units, but it's 32.
I think you're overthinking it. You're overthinking it because we start at 0, and this is acceleration, but it's starting from 0. Now you could do the acceleration formula, but at 1 second, it's going at 9.8 meters per second.
Right.
After 1 second. All right. So remember the pylon, 9.8. Then we add another 9.8. At 2 seconds, it is going to be going 19.6 meters per second. And at 3 seconds, 14, 19, it is going to be going at 29.4. So that's just like a really quick, surefire way of coming up with it. The other one will be at 32 feet per second, 64 feet per second at 2 seconds, and then 3, 6, 96 meters per second. Feet per second, I apologize. Okay. So when you're just dealing with a couple seconds, just do the addition. Running through the formula is probably going to get you in trouble, probably. When addition works, if it's just a couple seconds.
I got you.
All right. Okay. So we're clear up to that point, correct?
Yep, correct.
And like I told you, the way I teach physics, I spoon feed it to you, man. It's really not going to have a whole lot of guesswork, because what you have to do is you have to apply this. You have to put this into action when they ask you all kinds of funky questions on the test.
Sure.
All right. So now, let's go to the big screen. All right. So I think we have that down. All right. So now, what I want to introduce you to is the displacement formula. So, I'm going to attempt to, let's take our same tall building. Alright, you're up there, I'm down here. I decide to throw a ball upward, and you're going to take a picture with your video camera. Alright, so the trajectory, we're going to release the ball at, let's say, 80 meters per second. That's what we're going to throw it up at. That's the upward force. Now, what's going to happen? What do you think is going to happen to this thing eventually?
Well, eventually it's going to fall back down as a gravity.
So at some point, it's going to, at its apex, it's going to go to 0.
Right.
And then it's going to come back down, correct?
Correct.
Now, what we could do is we could use a formula to determine, after releasing it at an initial speed of 80 meters per second, I can find out where this thing is going to be at in 3 seconds. I'll just put 3s for 3 seconds. I can do that using the displacement formula, which is displacement is equal to v sub 0, which is our initial speed, times time, plus 1/2. You can use a or g for gravity, t squared. Now I know that looks crazy, but
times 1/2
a t squared.
Okay, got it.
Now there's a good side of this equation and there's a bad side of this equation. All right? Because in terms of this object gaining altitude, what is it going to fight us?
Gravity's going to fight us.
Okay, this is the bad side of the equation. And this is the good side of the equation. Remember the Wizard of Oz, the good witch and the bad witch?
Right, yeah, I remember that.
Okay, so when we take all this in terms, I'm at the bottom, I throw a ball up at 80 meters per second. I want to know how high this ball is going to get in 3 seconds. So basically all I need to do to find displacement is, I'll say displacement is equal to, what is our initial velocity, v sub 0?
80 meters per second.
80 meters per second times, we want to know where it's going to be at in 3 seconds, so we put the 3 there. 1/2.
Right.
Gravitational pull. What is gravitational pull?
Is that just 9.8 meters per second squared?
It's got to be negative because it is fighting us.
Okay, I got you.
And
That's right.
And we put 3 seconds in there and squared.
Do the camera over just to the right a little bit, just so I can see all of that. Make sure I got it written down. 9.8, and then the 3 squared, and that's just because of that's what we're trying to find out. So yeah, okay, I got it.
Okay. I'm just looking at my camera. I'm like, wow, that's a hell of a lot of panning.
Mm-hmm.
But no, I see it's necessary.
And basically, you just solve all that by order of operations.
So what would your answer be?
Well, I will tell you. Let me go ahead and do that real quick.
Mm-hmm. And use your hand because you cannot use the a calculator on the ASTB.
Okay, I have got 95.7.
I got the same thing. A lot of huh?
I love when a plan comes together, right?
Yeah, man. Yeah. So, okay, I'm trying to think of what my point was. All right. So it's very, very, very important when we do projectile motion questions. We have to keep in mind that gravitational pull is fighting against us. It's negative. We're throwing. Another example is a cannonball is shot straight up in the air. All right. We take a cannon, the barrel of a cannon, and we shoot it straight up in the air. We're going to have an initial speed, but gravitational pull is going to be fighting us all the way. It is the thing that is going to bring us to zero at the apex and then make the projectile return to the Earth. All right? So,
gotcha.
Very, very important. So, in 3 seconds, this object should be 95.7 meters away from us. Okay. Alright, let's see here. Okay, so was that clear?
Yes.
Okay. Alright, so now, in the same instance, now, what is going to happen to this equation? Alright, we're going to kill this because we got that already, because you're a superstar, man.
No, I'm not. I got a long way to go.
All my clients are superstars.
Gotcha.
Alright, so now, we're going to take me at the bottom out of this scenario, and you're going to drop the same object from the building. Alright, we're going to drop the same object. Now, something very interesting is going to happen to this Now we're releasing this object from the building. Something is going to happen to this formula. If you can see it, fine. If you can't, I'll explain it. But I just want to know if you can see it at first.
No, I don't.
Okay. What is the initial speed when you release the ball?
0.
0. So now can you look in this equation and see something interesting that's going to happen?
Well, yeah, the when you plug the initial speed in to the first part of it, it gives you a 0 on that part. If that's what you're referring to.
Mm-hmm. So when we drop objects from a building, the initial speed is 0. So 0 multiplied by anything is
0.
Very good. So in this case,
Uh-huh.
for displacement in this case, it will just be 1/2 AT squared. Make sense?
Does.
If it doesn't, stop me.
That's just for the initial speed. So.
Mm-hmm. So being that the initial speed is 0, this v sub 0 times time, it goes away and we just deal with 1/2 AT squared.
Right.
So now, I've got a fun question. And here it is. I sound like a game show host.
Here it is. Come on down.
I know, right? So what I would like to know, you're going to release a brick. Hopefully you never do that. But
Right.
you're going to release a brick from the top of the building. How far does this brick get away from you in 3 seconds?
That is going to be 96 feet.
I want to know it in meters.
Okay. Well, in that case, it's going to be 9.8 times 3. Always got to brush up on my basic math skills here, right? For some reason, these decimals always kind of throw me off, but it should be like 29, 29.4. I'm sorry.
Okay. Is that speed or distance?
Let's say after 3 seconds, how far is it falling?
Mm-hmm. Okay.
Maybe I need you.
What I would have preferred you have done is I would have just said displacement equals 1/2 9.8. Now why don't we make this negative now?
Right.
We did it for projectile motion. We made it negative. Why isn't it negative now?
Well, I don't know.
Because we're not throwing it upward and gravity's not fighting anything.
Okay.
Gravity's working with it now. But in this case, in this case for displacement, what I was looking for is 9 times 9.8 and then divide by 2. So
okay.
9, this is the 3 squared, which is 9. 9.8 times 9, 72, 81, 88 divided by 2. So when you drop this thing should have fallen 44.1 meters. Do you agree?
Yes, I see that. I see that now that you worked it out. So.
Okay. And if we use U.S. customary units, 1/2 times 32 feet per second, and then 9 seconds, or 3 squared, which becomes 9, which would be 32 times 9, 18, 28, and we divide that by 2, and that will be 144 feet.
Mm-hmm.
Okay, so when we release that object, after 3 seconds, 44.1 meters or 11.4 feet is how far that the object has gotten away from us. All right. So
I understand that now that you wrote it out like that, so I should.
So, and it's fine. It's fine. I understand what you were doing, but what you were doing was concerning speed. Because you were dealing with acceleration at 9.8 meters per second square and the 32 feet per second square. But as far as speed is concerned, in 3 seconds, we will have piled on, well, we worked it out before, but you could say 9.8 times 3. At 3 seconds, it would be 29.4 meters per second. And as far as U.S. customary units, 32 times 3, you worked that out, because I heard you say 96. So 96 feet per second. Okay?
It's just basically it just comes down to memorizing these different formulas and recognizing what the question is.
Dude, it's really not that hard. When you work out enough of these problems, it's really not that hard. I mean, I just look at it and be like, oh man, I never do it. But I know that initial speed times time equals 1/2 AT squared. Now, if I'm just dropping something, I'm just using 1/2 AT squared. I'm just dropping something. So I got to think, well, what is the difference? It's initial speed times time. That's all. V sub 0 times t. So it's easy to remember 1/2 AT squared. You know, just say 1/2 AT squared, displacement, if we're just dropping it from the building. And the difference between throwing a projectile upward or releasing a projectile, or we can't call it a projectile, or releasing the object and just let it fall, is this. We add a 0 to our initial speed, and that part of the equation is wiped out. So we're just dealing with the 1/2 AT squared. Now, man, you're going to be amazing at this. So let's just say you were strong enough, or no, you're on this side, I'm on that side. Okay. At the same time, we go 1, 2, 3. You drop a tennis ball, and I drop a brick. Which object is going to hit the ground first?
The brick?
Nope.
Ball?
Nope.
We hit at the same time.
Yep, they are both gonna. They're both gonna unfold at the same time because gravitational pull acts proportional to the weight.
Okay.
So, more weight you add, pretty much it doesn't even matter. The tennis ball and the brick will hit the ground at the same time.
Let me write that down.
Yes.
Same time if released at the same time. All right.
Okay. Now, a lot of times we talked about earlier. We talked about speed and velocity. All right. Were we just doing 1 hour, or were we doing 2?
Well, I was planning on doing 1 hour right now, but yeah, this is good. So this is very good so far because some of this, like I said, I never even did physics back in high school. So, but we could do 1 hour, then 1 hour tomorrow in the afternoon if you want to.
Yeah, because we're pretty much at the hour now. That's what I'm saying. That's why I was asking.
Yeah, that's fine.
Yeah.
So,
okay, so what I need you to do for this lesson is I need you to mark on your notes the number 10. Write the number 10 in velocity.
10.
Okay. But I just want to enter in some closing stuff, and then I'll turn you loose, and I'm not going to be like, oh, you owe me 15 minutes. I'm not going to do that.
Okay.
Damn it, Chase! I want my 15 minutes.
Right.
No.
Why am I writing the number 10 down though?
So I know where to pick up.
Okay, I got you. Okay, I got you.
No, that's not a bill for hours, dude. Okay. He's billing me 10 hours. No. No.
Woo.
I know, right? Okay. All right, let's get serious, damn it. All right, so a couple things I just want to cover. We talked about speed and velocity, and in formula, velocity equals distance over time, and speed equals distance over time. And you're like, well, what the hell's the difference? All right, because let's say you're driving down the highway in your vehicle. Don't laugh at my artwork. All right, you are going 55 miles per hour. That is a speed. When the cop gives you a ticket, how fast were you going? He or she writes down the speed, 55 miles per hour. Velocity is different because velocity indicates direction. So if I say you were going 55 miles per hour northbound on, where do you live at again?
Little Rock.
Okay, I-40. And we couldn't say northbound, we'd have to say east or westbound. All right. I-40 goes through Arkansas.
Right.
So that's why I asked, and so I could kind of give you something that kind of might mean something to you if you ever traveled on the I-40. I'm sure you have.
Many times.
But that's the difference. You could be going 55 miles per hour, period, and that would indicate speed, or velocity indicates direction. 55 miles an hour east. The plane is traveling 250 miles per hour northwest. All right. So that is the difference. And you could be asked that on the test. What's the difference between speed and velocity? Velocity includes or indicates a direction. All right, so that's how speed differs from velocity. In formula, you would use the same thing. You would use distance divided by time in both cases, whether you were computing velocity or speed. But the difference between speed and velocity is direction. Some other final notes I just want to get out of the way. All right. We talked about vectors, and that's going to tie us into our next thing, vectors. Now, if I drive a car off a cliff, you have to start looking at forces and being able to label them. So here's our little cliff, and here's our little water at the bottom, and our car drives off the cliff. A vector is a force. It's how we label forces. Okay, vectors have direction and magnitude. All right, so so it's going to be more than just speed. If this vehicle drives off the cliff at 50 miles per hour, we're going to have a vector going this way, aren't we?
Right.
All right, and as far as forces, what is another vector do you think will come into play in this situation?
I mean, obviously gravity's going to pull the car down.
Yes, we're going to have a downward vector.
Yeah.
All right. Now, on the Cartesian coordinate plane, remember our x and our y-axis?
Right.
What quadrant? This is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4. What axis do you think? Let's say if this is the origin, what axis do you think, what quadrant do you think we're going to wind up in?
You're probably going to wind up in the bottom right one.
Yes, in quadrant 4.
Quadrant 4.
So we have one vector, I'll put V1, and we have V2, and then I am going to label a special vector, and I will call this VR. R stands for resultant.
Resulted?
Yeah, it's the resultant because it's the final result of the two vector inputs. We have the 50 mile per hour force going horizontally, and we have gravitational pull acting in downward. And eventually we're going to wind up somewhere down here in the water line, right? You agree?
Yeah, my iPad All right.
Okay,
I
it's
got
cool.
this.
It's cool.
He's doing something weird. So.
Okay, so you see vector 1 and vector 2, that's the government. They're looking for the greatest physicist on the planet, and they track me through your camera.
I got you.
All right, so vector 1, vector 2 equals a resultant vector. Okay, and really, in essence, this is really the vector, the resultant vector. We put in a force this way, we put in a force this way, but this is actually the actual resultant vector. It's the result of the two vectors.
Mm-hmm.
Now, I keep saying I'm gonna let you go, but not yet. All right, so let's say this is like, I don't know. Let's say it's a river running through two land masses, and I have a 5 kilogram object. I'm holding it. Now, the trajectory of your vehicle is going to be like this, and the trajectory of my object that I release is going to go like this, right? So,
Right.
this guy's driving at 50 miles an hour, and this guy, me, I'm releasing an object of 5 kilograms. Let's say this is a 2,000 kilogram car. At the time that you drop, this vehicle leaves the cliff, I say I'm gonna release the ball at the same time. Is the 2,000 kilogram object gonna hit before the 5 kilogram object?
I mean, if you release the thing at the same time and they drove off the cliff at the same time, then yes.
Who's gonna get there first? I guess that's my more specific question.
Well, no, I don't think they're going to hit it at the exact same time. Because the other one's at an angle.
They would hit at the exact same time. Because gravity does not give a damn about the horizontal component. And like we said, on the two sides of the building, you got the brick. One person has a brick, one guy has a tennis ball. They drop at the same time. So once this leaves the cliff, and once this leaves my hand, even though it's 2,000 kilograms, it's 5 kilograms, the gravitational pull is still going to act.
Okay.
And it's going to act proportionately on each object. Now, how far it gets is a different example. I'm just saying, I'm talking about contact with the water. It may not get all the way across like that, but they're both going to hit the water at the same time, the splashdown part.
Okay. I got that.
Okay. So that is some initial stuff that you can grow on, because you have to look at forces. You got to see an object. I'm gonna give this Joel away because now I got my camera running now, and so let's say, and you're not being charged any extra for this.
Okay.
We have a table legs. That is the top of the table. I have a brick. I have a chain or some type of string attached to another brick. Now initially I am holding this brick up, but at some point, hold on, let me draw me. I laugh at my stick figures, I'm sorry. Alright, so I'm holding the brick at first, so there's no tension. Alright, so I'd like you to tell me all the forces you see at work. And I'll label them. And if you don't get them all, don't worry about it, it's okay.
Okay. Well, you have the gravitational pull.
Yes.
Of the
9.8 meters per second squared.
Right.
What else?
You have got I'll get, I don't know, you had to label.
I got you, man. I got your back. I told you, I got your back, homie. All right, 9.8 meters per second is acting downward. The brick is acting downward on the table. The table is supporting acting upward on the table. The table legs are acting downward on the floor. The floor is actually acting upward, supporting. There is tension pulling in that direction because this got gravity acting on it. Okay? Friction is acting in this direction because the friction between the brick and the table are at work. So it's producing a force in that way, in that motion. All right, brick. Well, at first we were supporting it, but after we let it go and it's in free fall, the brick will provide tension downward, which causes tension on the rope. Tension on the rope acts upward in that direction, but that's actually a co-partner of the friction causing that. So we'll circle that. That's debatable. Kind of, sort of. Well, as long as we see friction, then we will get tension on the rope. So gravitational pull, friction acting that way, trying to keep the brick on the table. You released it, and the initial speed is 0 meters per second. Now when we release it, then gravitational pull takes over, right?
Right.
Okay.